Good morning. We are Team Acumentrics Volta, and our project is automated variable load testing of high voltage DC output boards. Our technical director from Acumentrics is Brendan Smirbeck, a URI alum. Our team is comprised of 3 electrical engineers, myself, Hannah Ditto, Kyle Connell, and Daryl Grunewald. Acumentrics is headquartered in Walpole, Massachusetts, and was founded in 1994. Acumentrics is a preferred supplier of US-made power electronics to many of the world's largest defense contractors. They are also a trusted market leader in the rugged, uninterruptible power supply for harsh and combat environments, as well as autonomous power and heavy-duty industrial applications. The motivation in creating an automated testing system comes from the 1U blade series UPS being a complex piece of power equipment. The 1U blade has high power density and allows users to chain multiple units together. It is composed of over a dozen circuit boards with numerous responsibilities. With an automated testing system, the process becomes more efficient, thus saving Acumentrics time and money. The anticipated best outcome and extended best outcome was to create a functional prototype system that is capable of performing automated load tests of the DC to DC output board, the charger board, the DC front-end board, and the PFC module. The system must compare characteristics of each board to values sensed by the testing system. This is done through a data logging function in LabVIEW. The system will also visually indicate to the operator the results of the test. Our anticipated best outcome was achieved. This is Acumentrics' old or current testing system, and this is our testing system. The automated variable load testing will save Acumentrics thousands of dollars each year alone. Approximately 50% of the heat sink tests fail. 1,800 heat sinks were produced this year, and taking into account labor costs and testing time, Acumentrics could save about $1,400 per year. This is a general block diagram of our test system showing the LabVIEW structure on the left and the hardware and equipment on the right. I will be discussing the hardware portion. On the left, we have our test equipment. The Keysight data acquisition unit is used to read and control input and output signals. The benchtop low voltage supply supplies our low voltage signals to our boards. The Preen AC and DC power supply supplies our 200 volt input. And the BK Precision Programmable Load allows us to control the load current to the board when testing. On the right, we have our DUT enclosure interconnect, which has all of the cables connected to our equipment, which allows easy transition between boards when testing. The DUT enclosure provides a safe, high voltage testing area and cuts power to the board when the enclosure is open. Then we have our AC and DC solid state relays that are powered by the 5 volt benchtop source. These were necessary for the enclosure to function properly, and we have 2 relays so that the system can test AC or DC boards and still be safe. The data acquisition unit is a large part of our project and contains 2 modules. First, we have the 20-channel switch. When the switch is closed, that is what's being controlled, or the signal that is getting sent to the board. Channel 101 controls low voltage 2. Channel 102 controls low voltage 1. Channel 103 controls the AC solid state relay, and channel 104 controls the DC solid state relay. Then we have the multiplexer, which reads values. Channel 201 reads the output. Channel 202 reads low voltage 1, and channel 203 reads low voltage 2. For our system, the DAC is used in parallel with LabVIEW, in which Kyle will go into further detail.
Hi, my name is Kyle, and I'll be talking to you about how we use LabVIEW to reach our anticipated best outcome. LabVIEW is a software designed for any engineering application that requires test, measurement, or control. LabVIEW helped us directly reach our anticipated best outcome by helping us create a functional prototype system that is capable of performing automated load tests of the 1U blades DC output board and charger board. Specifically for our project, LabVIEW is used to simultaneously control our 3 testing units by creating block diagrams with each unit's individual LabVIEW drivers. Our three units are our data acquisition box, our AC and DC power supply, and our DC programmable load. Each unit comes with a set of LabVIEW drivers that are used to control the unit. For the data acquisition box, the LabVIEW drivers are used to measure voltage from the multiplexer module, as well as closing a channel digitally from the switch actuator module. This is our charger board data acquisition box VI. It starts off by initializing our data acquisition box to let LabVIEW know what unit is being used. From there, we close channels 101 and 102 to allow the small signal voltages to come into the board from the low voltage power supply. From there, we configure channels 201 and 203 to record our voltages. And from there, we use these values through a system of equations to let the user know if the board functions or not. If the output voltage is greater than 32 and less than 26, the board does not work properly. As well as if the small signal voltages are greater than 3.7 and less than 2.5, the user will be told to test the connections or adjust the low voltage power supply. These values are also used in the write to measurement file. The user will see the voltage values from start to end of testing in a text file. This will help the user know if there's a fail in the system. For the DC board, this is the DC data acquisition box VI. The code is exactly the same, except that the small signal voltages are at 15 and 3.3, meaning that we change the voltage tolerance to greater than 15.3 and less than 14.7, and greater than 3.6 and 2.9 will cause a failure in the system. We also write the measurement to a file to record all the voltages from start to finish of testing. The DC front end board data acquisition box VI. It is the exact same method, except the output voltage is between 205 and 195, and there are no small signal voltages. For the AC and DC power supply, we use LabVIEW drivers to deliver our input voltage to the boards manually from the code, allowing the user to have to do nothing besides making sure the connections are correct and running the code. This is the DC board and charger board AC/DC power supply VI. Start off by initializing the AC and DC power supply so LabVIEW knows which unit is being tested. From there, we use skippy commands to clear and set the output DC voltage to 0. From there, the voltage ramps up 5 volts every 50 milliseconds for 41 times, bringing the voltage to 200 volts safely. This is the code for the DC front end board, AC/DC power supply VI. It's the same method as the DC and charger board, except the input voltage is 28 volts, so we raise the voltage 2 volts every 50 milliseconds for 14 loops, bringing it safely to 28 volts. Our final machine that we use to achieve our anticipated best outcome is our DC programmable load. This unit is used to mimic a load that would be used by the 1U blade. We use this to see how the board works when it is drawing current from the board. This is the DC board and charger board DC programmable load VI. Starts off by initializing the loads into the LabVIEW so the LabVIEW knows which unit is being tested. The code is designed to ramp up the current from 1 to 19 amps every 2.5 seconds. It is also used to measure the output voltage and will tell the user if the voltage value is not at the correct values. If the voltage is greater than 32 or less than 26, the program will fail. The same thing goes for the DC front end board. The code is designed to raise the constant current from 1 amp to 19 amps, and the output voltage is 200 volts, so the tolerances are changed from 199 to 204. Daryl will continue talking about how we condensed all of our codes into one code. He will talk about the creation of our master VI and the use of our front panel communicating with the user.
One of the important aspects of this project was to create a system capable of automating the tests that current engineers at Acumentrics conduct, as well as simplify the flow of information. A big factor in completing this was creating a user-friendly interface for easy interaction. Here, you can see the UI we have created. It is designed to guide the test operator through the testing process, as well as visually indicate a pass-fail state to them upon completion of the test. Depending on the board being tested, the expected output values and relevant basic information can be seen in the top left corner. You can also see that depending on the state of the test, one of these LEDs will be lit, and that consists of running, pass, and fail. For the purposes of this presentation, they have all been lit up, but during the testing, only one is lit at a time. Toward the middle, there is a live feed of information for the duration of the test that can be observed. The operator can monitor the voltage, current, power, and relevant starting values that were recorded at the beginning of the test. Hand in hand with the designing of a simple interface, the more accessible we were able to make our work, the easier it is for Acumentrics engineers to change everything should they need to. Upon giving our work to Acumentrics to review and use for themselves, one of the problems was clumps of command that were hard to follow or understand. We have taken efforts to create sub-VIs in order to give ease of access to specific parts of block diagrams that focus on key tasks at hand. Here you can see a portion of commands that are responsible for determining whether the initial voltages present in the system meet the requirements by running through a system of equations. This has been condensed into a single block, which makes the main VI less cluttered and allows for simpler editing of the sub-VI. This is one example where we have taken this approach. We initially started out with puzzle pieces for each piece of hardware. As my partners explained before me, we used multiple pieces of hardware for this testing setup, meaning there are multiple things we had to communicate to. We started out by making each of these VIs for each piece of hardware and running them one after the other to complete these tests. We have since combined these VIs into one VI for each board. This means each board has its own VI and can be run when testing that board for the full testing process. The animation in this slide shows the flow of commands from left to right for one board in particular. Along with the previous point of combining the VIs into one for each board, we go a step further. We have created a master VI, as we like to call it. This VI is capable of calling to whichever board that needs to be tested. You simply open up a drop-down menu and select the specific test for the board that is currently set up. That board-specific VI is then called and run to completion. As more boards from the 1U blade have VIs completed for them, they can be added to this system for further simplified access and testing capabilities. Upon achieving our anticipated best outcome, we have been able to design a testing fixture that emphasizes high voltage safety through the use of an enclosure and relays which stop the test under non-safe conditions, selected appropriate and efficient hardware compatible with LabVIEW testing software, conducted testing for the sake of usable values in LabVIEW, automation of these testing processes by creating several VIs, a user-friendly interface that contains a pass-fail feature, and live feed information, as well as accessibility should anything need to be changed or edited. With that, Team Volta would like to thank all those who have made this project possible and for providing us with such a great opportunity to learn and grow as engineers. Thank you.